This is Dr. Shankaraiah from Department of Physics. In last presentation, I have discussed some topics in Module 4, which is magnetic and superconducting materials. And in today's presentation, I am going to discuss one more topic in superconducting materials. So that is BCS theory. So this is the topic of today's presentation, BCS theory. So what is this BCS theory and who developed this BCS theory and how BCS theory help us to understand this superconductivity? Okay. So in 1957, the American physicists Bardeen and Cooper and Schrieffer. Okay. So three American physicists in 1957. The three American physicists are Bardeen, B, Cooper, C, and Schrieffer, S. Okay. These three American scientists developed the quantum theory of superconductivity, which came to be known as BCS theory based on their names: B from Bardeen, C from Cooper, and S from Schrieffer. Okay, so BCS theory is basically Bardeen, Cooper, and Schrieffer's theory. This is the first quantum theory that is developed to understand the zero resistivity in superconductivity. So for these three American scientists who developed this quantum theory to understand the superconductivity, they awarded Nobel Prize in 1972. Okay, so they received, all these three scientists shared this Nobel Prize in 1972. So the BCS theory assumed interaction of two electrons through quanta of lattice vibrations. So what is this BCS theory is about? So this BCS theory is about to explain the zero resistivity in superconductivity, and in their theory they assume the interaction of two electrons through lattice vibrations. Okay, so they have explained the zero resistance in superconductivity through interaction between two electrons, and the interaction between these two electrons is occurring through the quanta of lattice vibration. So these two electrons are interacting because of this quanta of lattice vibration. So this is an important point or concept in BCS theory that explain the zero resistivity in quantum theory. So how does the interaction between two electrons through the quanta of lattice vibrations help or explain the zero resisting superconductivity? We will understand in this presentation. So this BCS theory explains successfully the effects of zero resistivity as well as Meissner effect. So the two properties of superconductivity are zero resistivity and Meissner effect. So these two properties of superconductors are explained successfully by this BCS theory, which is Bardeen, Cooper, and Schrieffer's theory, and this is a quantum theory that explains this superconductivity and the properties of superconductors, namely zero resistivity and Meissner effect. The two principal features of BCS theory are electrons form pairs. Okay, the two principal features of BCS theory. So the BCS theory, what are the two important concepts or two features of BCS theory? The first feature of BCS theory is that electrons form pairs, and these pairs are called Cooper pairs. Okay, and which propagate through the lattice. So basically we are considering a conducting material, and conductors or metals have free electrons, and these free electrons can form pairs. Metals which have free electrons, and these free electrons can form pairs, and these pairs are called Cooper pairs, and these pairs are propagating throughout the lattice, right? So we are to understand this metal, we are thinking that in theory we are taking a lattice, right? So lattice is nothing but the arrangement of atoms in a regular periodic manner, right? Okay, so atoms are sitting in on a lattice, and so each lattice point is occupied by an atom. Okay, and these atoms, we are taking a metal or conductor, these atoms have free electrons, and all these free electrons are running through this lattice. Okay, so that is why the first important feature of BCS theory is that the free electrons which are there in conductors or metals, they form pairs, and these pairs are called Cooper pairs, and these Cooper pairs propagate throughout the lattice. The second feature of BCS theory is that such propagation, right, we are saying that these Cooper pairs are propagating throughout the lattice. So such propagation is without resistance because electrons move in resonance with phonons. So when these Cooper pairs are propagating throughout the lattice, this propagation has no resistance. This propagation, when these Cooper pairs are propagating through this lattice, they have no resistance, so that is zero resistance. Because electrons move in resonance with phonons. That means that zero resistance. When we discuss these conductors, resistivity in conductors, we said that even at 0 Kelvin, for example, so this is resistivity or resistance in conductors with temperature, right? So when we were discussing about this resistance in conductors with temperature, we found that as we lower the temperature, the resistivity or resistance decreases. But even at absolute 0 Kelvin, the resistance is not zero. There is some residual resistance, right? So this residual resistance is coming from the scattering of electrons. But in superconductors, when these electrons, free electrons, form pairs, which are called Cooper pairs, these Cooper pairs are going to propagate in resonance with phonons. Phonon is nothing but a lattice vibration, right? Because these Cooper pairs are propagating in resonance with phonons, there is no resistance. That is how we are going to get zero resistance in superconductors. Okay, so what is a phonon? Phonon is a quantum mechanical description of an elementary vibrational motion in which a lattice of atoms or molecules uniformly oscillate at a single frequency. Phonon is a quantum mechanical description of elementary vibrational motion. Okay, phonon is nothing but the lattice vibration. Okay, so this phonon is a quantum mechanical concept. This phonon is a quantum mechanical concept where we are saying that phonon is lattice vibration, and where the lattice of atoms or molecules uniformly oscillate at a frequency. Okay, so when the lattice vibrates, so when these atoms vibrate with a single frequency, and such a vibration is called as phonon. Okay, so these electron pairs, the electrons which are present in metals, they form pairs called Cooper pairs, and these electron pairs propagate in this lattice in resonance with phonons. Okay, so that is how we are going to see the zero resistance in superconductivity. Okay, so these are the two important features of BCS theory. The first one is that the free electrons which are present in these materials form pairs, and these are called Cooper pairs, and these Cooper pairs propagate throughout the lattice. Okay, so that is the important feature of a BCS theory. The second important feature of a BCS theory is that when these Cooper pairs propagate in the lattice, they propagate in resonance with phonon, and hence there is no scattering of the electrons, and hence we are going to see the zero resistance of superconductor because of this scattering of because of the zero scattering of the electron pairs are called Cooper pairs. Okay, so yeah, so these are the two important features of BCS theory. So to appreciate this BCS theory, to appreciate the formation of Cooper pairs in BCS theory, let us consider this. Okay, so now so we have atoms, right? So let us draw this lattice. Okay, so now we have a lattice. So I am taking two-dimensional lattice to explain or to understand for the convenience. So it is easy to understand. Okay, so this is atom, this is an atom, this is an atom. So all atoms are sitting in lattice point. So this is actually a lattice. So I am not drawing the lines, but this is a lattice, two-dimensional lattice, and these are all the points. These are the atoms that are sitting at lattice points or lattice sites. Okay, now. So when these atoms are losing, so these atoms have free electrons. So this is positively charged ion because they have lost one electron which is loosely bound to this atom, so that is going to move freely in the system. So once they are losing this boundly loosed electron, they are going to become positively charged. So you have all positively charged atoms at the lattice sites, right? So these are all positively charged atoms because they lost their electrons which is loosely bound. Okay, now all the free electrons are going to move in this lattice, now. Okay, so when electron comes closer to any one of these positively charged ion, electron is negatively charged and electron is negatively charged, and this ion is positively charged, right? So when electron come closer to this ion, so because of these are oppositely charged, they are going to get attracted, right? So they are going to get attracted. Yeah, so they are going to get attracted as the electron comes closer and closer, to this ion. As it comes closer, and another electron from this side also, if there is an electron this side, this electron is also negatively charged and ion is positively charged. They can, when they come, this is positively charged ion, these two are negatively charged electrons. So because of they are oppositely charged, they are going to get attracted to a positively charged ion, right? When they come closer, these see each other, these two negatively charged electrons see each other, and then they repel, right? And they repel, or they repel, and that is how this ion will vibrate. This lattice, or this positively charged ion will vibrate, and these electrons, so as when they come closer here, again they will attract to this positively charged ion, and again they will repel, and again they will propagate. They will come to closer to this ion, again they will attract and repel. So these atoms will vibrate because these electrons are coming closer and closer, they will vibrate. So this is what is called lattice vibration or phonon. Phonon is nothing but lattice vibration, and these electrons are going to come closer and they are going to form a pair, and they are going to become a Cooper pair, and then again as they go closer to the another positively charged ions, so they will come closer and closer. So that is how these Cooper pairs propagate in this lattice through this phonon. Okay, so we are saying that the Cooper pair, the formation of this Cooper pair is only because of this phonon or lattice vibration. Because of these electrons, two electrons are of same charge, they will repel, but because there is a positively charged ion sitting on the lattice side, as these two electrons come closer, these ions will vibrate. Okay, so because of this vibration, when these phonons will propagate through the lattice. So the propagation of Cooper pairs is only through this phonon, which is known as lattice vibration. So you can see this the propagation of Cooper pairs through the presence of this positively charged ions. Okay, so through the lattice vibration. So in this model, two electrons propagate along a single lattice row. Each electron experiences an attraction towards its nearest positive ion, as I discussed, right? So each electron is negatively charged, and this positively charged ion is sitting at the lattice site. So they both will get attracted to this positively charged ion. When the electron gets very close to each other in the region between ions, they repel each other due to Coulomb force because they are same charge. Okay, so then again they will come because there is another lattice site, and at each lattice site there is positively charged ion. Okay, so again they get attracted to this positively charged ion. As they come closer, they will repel. So that is how these Cooper pairs propagate in this lattice through vibration of the positively charged ions. So in an equilibrium condition, a balance between attraction and repulsion is established, and the two electrons combine to form a Cooper pair. When there is in equilibrium condition, a balance between attraction and repulsion is established. Attraction between positively charged ions. So you have positively charged ions. All these positively charged ions are sitting on lattice sites, and you have negatively charged electrons. These electrons are free in the lattice, and they can move. They can move throughout the lattice, right? So when in an equilibrium condition, the repulsion between two electrons, and the attraction between electron and positively charged ion is established. When there is a balance between attraction and repulsion, the two electrons combine to form a Cooper pair, and then they propagate through this lattice vibration or through because of this phonon. Okay, so at normal temperatures, the attractive force is too small and pairing of electrons does not take place. At normal temperature, at room temperatures, the attraction between positively charged ion and negatively charged electron is too small. So the attraction is too small at normal temperatures, so you don't see a formation of Cooper pair. But however, at lower temperature, as we decrease the temperatures, we see such pairing is energetically advantageous. So we will see the formation of Cooper pairs only at very low temperatures, as the attraction between positively charged ion and negatively charged electron is strong. In a typical superconductor, the dense cloud of Cooper pairs form a collective state, and the motion of all the Cooper pairs is correlated. See, this is how a single Cooper pair form, right? So there are many electrons and there are many lattice rows, so there can be many Cooper pairs. You can see, so in a typical superconductor, there is a cloud of Cooper pairs form a collective state. So you see, in each row there is a formation of Cooper pair, and they are all propagating throughout the lattice. So there is a formation of a collective state, that is ordered state of all these electrons. Okay, so this happens only with low temperatures, because the attraction between the positively charged ion and negatively charged electron is strong only at lower temperatures. Such pairs drift cooperatively through the materials. So thus the superconducting state is an ordered state of conduction electrons. Conduction electrons are free electrons, right? So since the density of Cooper pairs is very high, because there are many electrons which forms Cooper pairs, these Cooper pairs are the density is large, very high. Even large current required a very small velocity, because the Cooper pairs are large number present in the lattice. Even if you want large currents, they require a very small velocity, because there are so many number of Cooper pairs are present. So the small velocity of ordered Cooper pairs minimize the collision process and leads to zero velocity, zero resistance. So how do we get zero resistivity in superconductors? Because we can understand the zero resistivity of superconductors through the formation of Cooper pairs. And because of these Cooper pair density is high, even if you want large currents, they need only very small velocity. Okay, so because the Cooper pairs are moving with very small velocity, there are no collisions or no scatterings. Because of this zero scattering or very small velocity of these Cooper pairs will give rise to the zero resistivity in superconductors. So the electrons of a Cooper pair have a lower energy than unpaired electrons. When we have free electrons in these materials, when you look at the energy of this state where you have free electrons, the energy of the state where we have free electrons, and when we compare the energy of the state where you have Cooper pairs, we find that the energy of the Cooper pairs is lower compared to the energy of unpaired or free electrons. So always system try to lower its energy to go to the lowest energy state. So we find that the Cooper pair state is the lower energy state, and hence we find the zero resistivity in superconductors. So this BCS theory predicted the existence of an energy gap between the ground state, which is a superconducting state, and first excited state, as you can see here. So there is a energy gap between the superconducting state, which is a ground state, and the first excited state. So this delta is the energy gap. The energy gap represents the energy required to break the Cooper pair. So what do you mean by energy gap? If you want, there is a formation of Cooper pair in these superconductors. If you want to break the Cooper pairs and you want to make them free, you need to supply some energy. So energy gap represents the energy required to break up a Cooper pair. Okay. Hence, larger energy gap corresponding to more stable superconductor. If there are many Cooper pairs, and the energy gap between the ground state, which is a superconducting state, and first excited state, if the energy gap is large, we need to supply more energy to break these Cooper pairs, right? So then if the energy gap is large in a superconductor, then those superconductors are very stable. Okay. So according to BCS theory, the energy gap at 0 Kelvin is given by this equation, which is equal to 2 delta. Delta is the energy gap, and that is around 3.52 KTC. This TC is critical temperature, and which will be roughly equal to 10 power minus 3 electron volt. So this is the range of energy gap in superconductors as per BCS theory. Okay. So to summarize, in this presentation, I have discussed the BCS theory. So in this presentation, I have discussed BCS theory. BCS theory is nothing but Birding. This theory is given by 3 American scientists, Birding, Cooper, and Schrieffer. Okay. So these 3 scientists developed a quantum theory to explain the zero resistivity in superconductors. They explained this zero resistivity in superconductors through formation of Cooper pairs. So they explained this through Cooper pairs. Cooper pairs are nothing but a pair of electrons, and Cooper pairs through phonons. Cooper pairs through phonons. So so the 2 important features of BCS theory is that the free electrons form pairs which are called Cooper pairs, and these Cooper pairs propagate throughout the lattice, right? And the second point is that these Cooper pairs propagate throughout the lattice in resonance with phonons. Phonon is nothing but lattice vibration. Okay. Through this lattice vibration only, these Cooper pairs propagate through lattice, because there is a high density of these Cooper pairs. High density of Cooper pairs in these materials. They need, even if you want more large currents, these Cooper pairs need very small velocity, and hence the small velocity of these Cooper pairs leads to zero collision and no scattering, and hence we get zero resistivity in superconductors. So the zero resistivity in superconductors is explained or is understood. Zero resistivity explained by BCS theory successfully. Okay. So the zero resistivity in superconductors is explained successfully by these 3 American scientists, Birding, Cooper, and Schrieffer, in which they developed a quantum theory in which they explained that there is a formation of Cooper pairs, and these Cooper pairs propagate throughout the lattice through phonons. And because of there is high density of Cooper pairs in these materials, they need a very small velocity, and because of this small velocity of the Cooper pairs, there is no collision between these electrons, and hence we understand this zero resistivity that is present in superconducting materials. Okay. So I am closing here. I am closing this presentation here, and in the next presentation we will discuss about the next topic in superconductors, that is about applications. So what are the applications of superconductors? So that we will discuss in the next presentation. So with that presentation, we will close this superconducting materials, and then the last presentation in here will be the numerical problems on superconductors. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.